All right, section 7.1 was an introduction to decimals. Section 7.2, we're going to take a look at doing operations with decimals. And the first operation we're going to do with decimals or operations are addition and subtraction. So with addition and subtraction, we're going to line up the decimal points and we're going to add and subtract as with whole numbers. So we're going to consider 4 and 33 hundredths and 3 and 26 hundredths, and we're going to add them together. So we're going to do it the way that this is describing first, and then we're going to answer this question of why does this work? Why is this the process? So this is what we said we were supposed to do, which was to line up the decimals. And then we're going to add just like we would have with whole numbers. So we're going to start on the right and we're going to move to the left. That's our traditional algorithm. There's others that we do in number theory too. You could do those, but this one's pretty nice. I have 9, I have 5, and I have 7. So I have 7 and 59 hundredths. Okay, good so far? But why does this work? This actually works because of what those place values are. And we can show it in lots of ways. So I'm just going to show you one of them. And I'm going to harken back to what we did in chapter 6 when we were working with fractions. So if I have 4 and 33 hundredths, I'm going to write that as 4. I'm going to write this as 3 tenths. And I'm going to write this as 3 hundredths. Does that make sense? Okay. And then I'm going to also have 3. And I'm going to have 2 tenths. And I'm going to have 6 100ths. All good so far? And then the pieces that are like, or like terms, they are like one another, we can add together. So here's a 7. I have 3 tenths and I have 2 tenths. Those are alike because they have common denominators. That gives me 5 tenths. Okay, that's really sloppy. Let's try that again. That's better. And then on the last one, we have 3 hundredths and 6 hundredths, which makes 9 hundredths because the denominators are the same. And then going sort of backwards from this fraction notation into decimal notation, this would be 7 and 5 tenths and 9 hundredths or 59 hundredths. Okay, certainly not the only way to justify why we're adding and why these things work, but it is a really nice application of seeing how the fractions and the decimals are corresponding and work together. Okay, so we're going to do an example. A stock's price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of this stock? So, what operation are we doing in this problem? We are doing subtraction. So we're going to take our $63.28 and we're going to subtract $27.45. And in doing so, we need to line up the decimal, which I did when we do our subtraction. We're going to work our way down from right to left. 8 minus 5 is 3. And the next place over, I can't take 4 away from 2. So what I have to do is to regroup. Now what I'm physically doing is I'm taking essentially a dollar bill. Okay, this is a $1 bill. I'm going to take away one of the $1 bills, and I'm going to turn my $1 bill into dimes. That's what I'm doing. And I'm going to get 10 dimes plus my 2 dimes. That gives me 12 dimes. Okay, I know this is just called borrowing or it's called regrouping, but that's physically what this means in this context. Right, I'm turning a dollar into dimes. So now I have 12 minus 4, 12 dimes minus 4 dimes, which I'm perfectly capable of taking those away at this point. That gives me 8. And then I have to do it again because now I have $2 minus $7. There's not enough there. So we're going to have to do it again. We're going to take this 6 tens, and I'm going to borrow a 10. Right? I'm going to regroup a 10. There will be 5 tens left over, and I'm going to turn the 10 into 10 ones. Well, I have 10 ones plus the 2 ones, so now I have 12 ones. So I have 12 minus 7 is 5, and then 5 minus 2 is 3. So the decrease is $35.83. Okay, I realize I'm belaboring the idea. You understand how to borrow and to regroup. You've been doing this since you were quite young. But there is a reason behind why that's working. We talk about it in depth in number theory, but not all of you have had number theory, and so I want to give you just a little taste of the why on that. Is that all right? Excellent. Okay, the next one, which is honestly the more tricky one to justify, is the multiplication. So with multiplication, we're going to multiply the way we would with whole numbers, And then we're going to count the number of places after the decimal point in all of the factors. And this will be the number of places after the decimal point in your product. There's no lining things up. This is what my children want to do in my house. They really want to line things up like they do with addition and subtraction. We line things up a lot. These actually do line up, but it's irrelevant that they do. Okay, it doesn't matter that the decimals are on top of each other or not. So what we're going to do is we're going to do it with the description, and then I'm going to show you why it works. So what is 7 times 3? 21, and that's all I have to multiply in this problem. If I had more steps to multiply, I would keep multiplying like I would normally, right? And with the whole numbers, that's fine. The part that people get tripped up on is that I can't just take the decimal point and drop it down. This is not 2.1, okay? I have to count how many places behind decimal points exist in the factors that I just multiplied. There's 1 in the decimal point with 0.3, and there's 1 in the decimal with 0.7. There are 2 values after decimals. So I need 2 values after my decimal point in the number 21. So that means that the decimal has to go in front of the 21 because I need 2 numbers after the decimal. Okay, this is a statement. It is absolutely true. We didn't do anything wrong, but it begs the question, why? Right? Why couldn't I just pull the decimal down below? And just because it doesn't give me the right answer is not a very good justifying, that doesn't feel like enough. And it really isn't enough, right? It doesn't give me the right answer, but why does it not give me the right answer? Well, fractions actually are very helpful to justify why this doesn't work. What is decimal point, the 0.3, right? What is 3/10 as a decimal? Well, it looks like 3 over 10, right? What about 7/10? 7 over 10, okay? How do we multiply fractions? Well, we multiply across the top and we multiply across the bottom. So what is 7 times 3? 21. What is 10 times 10? 100. What is 21 over 100 in decimal form? Well, it means I need 2 decimal places, right? Because it's the number 100 and the 21 goes in them. This is 21 hundredths. Whether you read it properly here, 21 over 100 as 21 hundredths, or you read it properly over here, 21 hundredths from a decimal point perspective. Okay, division is a little bit more straightforward, but again, it begs the question and we will justify why. So with division, we're going to make the divisor into a whole number by moving the decimal point in the divisor and dividend an equal number of times. And then we're going to divide the way we do with whole numbers. Okay, so the divisor is the number you're dividing by. It's the 0.5. Okay, so I'm not necessarily concerned with getting rid of all decimals, just the decimal point and the divisor. Well, there's only one decimal point in this particular divisor. So I only need to move it one time, which means when I move this one time, I still have, a decimal. That's okay. I can have a decimal, but I don't want the decimal to be in the divisor. Once it's in this form, we can actually do the division the way that we would work with in whole numbers. So I have 5. It's dividing itself into, or it's being divided by 5. So 7.5. So how many 5s are there in 7? 1, right? 1 times 5 is 5. Subtract, I get 2. I'm going to bring my 5 down. The decimal point goes straight up in my division. I don't really need to put the decimal point down here. I'm treating this like a whole number. How many 5s are there in 25? 5. And so my answer is 1.5. Okay, so again, but why? Why does this work? Well, let's take a look at what happens if we think about it in terms of fractions. So I'm going to move this all over so you can see the fraction part of it next. So if I write 75 hundredths as a fraction, it would be 75 over 100. Correct? Okay. Actually, let me write it differently. I'm going to take it back. Let's do the division part first. Just to write it as a fraction like this first. I think that's a little bit better. The other way works, but this is a little bit cleaner. All right, this is what it means to divide. I've just written it in fraction form. I don't want the decimal on the bottom. I want to move it over. But the way I get decimals to move is I actually multiply by 10. Multiplying by 10 moves decimal places. When I have 0.5, it would be like having 50 cents. And if I had 10 times 50 cents, that would be $5. So a 5 on bottom. That gives me the 7.5 on top. And all of a sudden, it now looks like this form, doesn't it? It actually looks like 7.5 divided by 5. It's just written in fraction form instead of in the division, like house form. Okay. The next thing in this section, as it relates to operations on decimals, is scientific notation. So the basic form in scientific notation is a times 10 to the n, where a is in between 1 and 10. It could equal 1. It can't equal 10. So greater than or equal to 1, but less than 10. And n is an integer. So where do you see scientific notation used? Somebody should say science. Okay. What kinds of things in science do you see scientific notation used for? In chemistry. What kinds of objects are you using them for in chemistry? Do you know? In chemistry, it's usually really small objects. Very, very small. Biology as well. Very, very small things. As in, like, they're a decimal point with some zeros maybe, and then you have some numbers, right? Cells, atoms, molecules, things like that when we're talking chemistry and biology. So scientific notation can be used for things that are very, 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 very small. It can also be used for things that are very, 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 very what? Big, right? Think in terms of astronomy, like distances to things, right? Like solar system kind of stuff, right? How far is it from here to the sun, from here to, Neptune, whatever. There's something looking at things on a very, very, very large scale, right? That's where you see scientific notation used. Scientific notation is not used to report how much money is in your bank account. We don't use it that way. So if you're creating a problem with scientific notation, make it authentic so that it actually makes sense, right? It's annoying when you see math problems that are using something just for the sake of calling it a word problem, but they're completely out of context. We won't use scientific notation for just every kind of number. There's specific things for which it's used. We want to be able to, however, change both in and out of scientific notation, to use it or to not use it when it is or it isn't appropriate. So the way that we're going to move standard numerals into scientific notation is the following. We're going to move the decimal point to create a value between 1 and 10. We're going to count the number of moves that we made. A positive exponent means that you had a large, as in larger than 10, number. And a negative exponent means you had a small, as in smaller than 1, number. So our definitions of large and small are based on 10 and 1. Bigger than 10, large. Smaller than 1, small. Okay? You can talk about moving things left and right. I don't talk about moving things left and right. And the reason that I don't is because it depends. Do I move it left or do I move it right, depending on if I'm moving into standard or out of standard, into scientific notation or out of scientific notation. And it can become very confusing. But if you will remember that positive exponents are big numbers and negative exponents are small numbers, it allows you to go either direction, depending on the context, without having to think about left versus right. So here's an example. We have 298,000, and we want to put it into scientific notation. Is this number a big number or a small number? It's big. Okay, so it's important for us to recognize that we're dealing with a big number here. I mean, obviously their number's bigger. That's not the point. But it's bigger than 10, so it's going to be big by our description right now. So the decimal point right now doesn't sort of appear to be anywhere in this number, which means it's at the end of the number. And we want to move that decimal until I have a number that's between 1 and 10. Where will the decimal's final resting place be? It needs to be between the 2 and the 9. If it's between the 2 and the 9, I have the number 2.98, and that number is between 1 and 10. So I'm going to count. I'm going to count how many times do I have to move the decimal to get it there. 1, 2, 3, 4, and 5. So I have 2.98 times 10 to the 5th. Big number, positive exponent, so it's positive 5. If I'd had a small number, I would have had a negative as my exponent, but I don't. Okay? Yes, ma'am.
I don't know if this might be a stupid question, but like, if we have the 0.98, why is it still to like the 5th power? Like, if we only have three more zeros after that. Does that make sense?
Yeah, it's because the decimal point doesn't count to the end of the number. It counts its location where it already is. Like, this is like $2.98 if you think about it money-wise, right? So $2.98 and $298 are not the same thing. So the decimal, or that number 5 is telling you how many decimal places you'd have to move to turn it back into another number if you were turning it back into standard notation. Okay, so we don't get the 2 that are there for free just because the numbers show up.
Okay.
Yeah. All right, scientific notation the other direction. We can take our scientific notation and turn it into standard notation. So scientific notation looks like numbers like this, right? 2.98 times 10 to the 5th. And turning it into standard notation will be the opposite of what we just did. So we're going to move the decimal point the number of places indicated by the exponent. If we have a positive exponent, we get a big number. And if it's a negative exponent, it's going to be a small number. Well, that tells me how the decimal has to move. Left or right, depending on whether it needs to be big or small. Okay? So we're going to take our number 3.2 times 10 to the negative 5. Apparently 5 was what I was just really in the mindset of doing when I was doing these. Got some 5's exponents everywhere. So I have 3.2. I'm going to write it here again. This has an exponent that says negative 5. Because it's negative, will it be a big number or a small number? This is a small number. So if I'm supposed to be getting a small number, which direction does my decimal point need to move to make this number look smaller? To the left. Yeah? If I move it to the right, it's going to become 32 or bigger. That's a big number. I want it to move to the left. How many places is it going to move to the left? 5. So the first place I get sort of, because it's there, I can see it. That's one place. I need some more place values to move, right? So I need some places to move in here. And I can just put a bunch of random zeros if I want, more than necessary if you need. But I need to move it 5 places. So I've already moved it 1. Then I've got 2, 3, 4, 5. And if you wish, here's the decimal point. If you wish, you can have another number 0 in front of that. It's sort of optional. So you can either write 0 point. I've got 4 zeros, 3, 2. Or if you want to write it with the decimal point with the 4 zeros, 3, 2, that's fine as well. It's a small number, right? It is a small number. Okay, let's take a look at how we do operations with scientific notation. So we're going to write the result of the following. Notice it has 8 times 10 to the 12th and 6 times 10 to the 15th. And so this is much like one of the earlier problems I did where we're going to group the things that are together alike. So the 8 and the 6 get grouped. So I have 8 times 6. And then the 10 to the 12th and the 10 to the 15th get grouped like such. So what is 8 times 6? 48. And then what happens when I have 10 to the 12th and 10 to the 15th? We did this back in chapter 6. You add the exponents. So if I add these exponents together, what am I going to get? 27. Okay, we've done the operations. We do not have a number in the form we're supposed to have it in. This number is not in scientific notation. Why not? What is it? It's not because there's not a decimal. We don't necessarily have to have a decimal. 48 is bigger than 10. That 48 is supposed to be between 1 and 10, and it is not. Right? So I need to change the 48. I need there to be a decimal point here. I need it to say 4.8. But I can't just go changing 48 into 4.8. There's got to be some compensation for having changed that. What happens is that since I made the decimal that was big, right, it was a big decimal, I need to make my exponent bigger by 1. I moved the decimal point 1 place. I'm going to put an X here for the moment since I've got so many dots going on. This will be a 28. It increased by 1 because I moved the decimal point 1. It increased as opposed to decreased because it was a big number. Okay, so the exponent got bigger. That's a great place for us to stop.